So what we did last time is we have taken this beam splitter. So beam splitter, as I said, it is like a mirror, but you have some, it's not perfectly a mirror, the light can pass through this thing. So here you have this input light. So these are two modes quantum mechanically, and then you have output next, right. So if I call it as A, this is A prime, these are the field operators, A prime dagger, this is B and B prime B dagger, this is B prime and B prime dagger, right. And this we have seen that if I take this as a 50-50 beam splitter, so which means that this this beam splitter matrix, which is theta epsilon phi, which is like e to the power I epsilon cosine theta, e to the power I phi sine theta, then minus e to the power minus I phi sine theta, and then e to the power minus I epsilon cosine theta. If I take this beam splitter matrix, which is a unitary matrix, then I take basically theta is equal to pi by 4, epsilon is equal to phi is equal to 0. Now, one could take other phases also, but let's, for simplicity, this is the thing. Then what we have seen is that if I take here a single photon state and here also a single photon state, then this state will be of this form 1 upon root 2, maybe it is 2 comma 0 minus 0 comma 2, right. So, therefore, if you put detectors here, then either 2 photons come here and 0 photon, or you will have 0 photons and 2 photons, right. There is nothing else you can get to see. So, this result we got through the rules of quantum theory. Question is, how will I interpret it? So, this is the matrix, this is the transformation, this is a unitary matrix, 3 parameters. So, unitary matrix 2 cross 2 unitary matrix of determinant 1 can be represented by 3 parameters, right. So, this is a fully general 2 cross 2 unitary matrix with determinant 1, right. And so, the field operators will change like this. So, A prime and B prime, it will be like B theta epsilon phi, this is a matrix acting on A and B, right. This is how it changes. I mean, just you take 2 by 2 matrix. So, this is how it changes. In fact, this is equivalent to the the unitary representation of this B. Of course, you will have to take the dagger, because you will have to work in the Heisenberg picture, okay, A and U B, and then U B dagger B U B. Okay, this is the infinite dimensional unitary representation. So, let me try to understand what is going on here. So, as I said, classically you can also have situation where one photon comes here and one photon comes here, and as Anupam said last time, that this scenario, this event is more probabilistic compared to these two. Why? Because this is a 50-50 beam splitter. So, the the probability that 2 photons go here and nothing here is 1 upon 4. Similarly, the probability that classically probability that 2 photons go here and nothing here is 1 upon 4. So, remaining probability, which is half, will be 1 photon here and 1 photon here, right. So, classically this is more probable, but quantum mechanically this probability is 0. This is of course 50-50 beam splitter. So, let us try to understand what is going on. So, there are 4 possibilities of these 2 photons when they come inside this beam splitter. Okay. So, one possibility, so let me take another color, perhaps then things will be easier. So, 4 possibilities are that so maybe I will use this one. Okay. So, this is your photon, single photon. It is coming in this. Of course, I should not draw in this way quantum mechanically, but to make things easier, and then it gets reflected inside the beam splitter, right. So, you will have a photon here, and similarly you can have so it is like okay. So, this is one possibility, and this corresponds to one photon here, one photon here. This you know it that cannot happen. Okay. Is this clear? Okay. The huh? This is this. These are the two, right?
Okay, incident photons you have. Okay, I got to.
I mean, this pictorially, you know. The other possibility is that
Red one goes down and yeah, and blue one goes right.
okay. So, this is also this case that you have one photon being detected here, one photon being detected here. Okay. And these two cases we are not considering, they do not appear here. The third possibility is that okay. And then this is fourth possibility. So, 2 photons are coming in this detector, and here 2 photons are coming in this detector. Okay. So, there are these 4 possibilities. Is it clear? Right. So, what we get to see is only these 2 possibilities. Okay. So, yeah. So, basically according to our convention, 2 photons coming here and 0 photon coming here. So, we call it as this is this incident, okay, and so I will call it like this, and then 0 photon coming here and 2 photons coming here. This is this event, okay.
So how do we go from this quantum nature to classical nature?
Which is quantum nature and which is
I mean,
classical
you were
nature?
saying that that one photon will go in either direction.
No, outside this is the case, right? Outside of the beam splitter, this is of course the case, right? Like here, outside this is of course the case. This because these photons are distinguishable in this case, right? Because they are going through different paths, so they are distinguishable. When it comes outside of this beam splitter, again they become distinguishable. The problem is inside this beam splitter, because that is a localized region. And we know that photons are indistinguishable if they are wave functions do overlap, right? So, inside this beam splitter they will become indistinguishable. So, outside of this they are anyway distinguishable, you do not have any issue, but inside this beam splitter. Okay. So, this is a pictorial one, of course photons do not take straight line, this is a wave function is there, they are moving. So, this is just to understand what is going on. Okay. So, this is just a pictorial one, I mean do not think that this is actual path. Okay.
No, I was saying that previously you said that Anupam said that normally what we have happens is one photon goes here and one photon goes down and one goes right. So this is what classically happens.
Yes.
And in quantum mechanically we are seeing that two photons are going in.
No, that is a, because this is a unitary transformation quantum mechanically. Classically also if it is lossless, that is a lossless, I mean energy preserving transformation. So, quantum mechanically it is also energy preserving, but I said that to get a proper picture, it should be on the top of energy preservation, it should be mode preserving also. So, therefore, 2 input mode should go to 2 output modes. Okay. So, mode preservation is there. Now, what I am drawing here is nothing to do with this. So, mode preservation is of course there, right. So, these paths are of course not actual path, but to understand what is going on inside the beam splitter, that is what my intention is, to see what is the problem, why you are not getting one photons here, one photon here, this event why it is not occurring.
Left board picture is anyway not possible.
Sorry?
The left board picture is not possible in quantum world.
Yes,
That
it is
your
not
point.
possible in this
And now
case.
you will explain that.
Yes. So,
why
the point is that, yes, so what is the problem? So, we will have to take a phase convention. So, the phase convention is that if photon passes through this, that means it transmits, then we will have a basically a negative sign, it will take care. I mean this is just a convention, you can choose any other convention also. So, if light passes through here, photon for example passes through, that means transmits from this side to this side, it will acquire a negative phase. Okay. That is just a convention, you can take some other convention also, it is just a convention, and for nothing else I am taking such phase convention. So, for all other paths there is no change in phase. Okay.
So that would be relevant for us.
That would be relevant for us. Okay. So, you see that in this case, according to our phase convention, it should be like there is no change in phase, there is no change in phase because both are reflected. So, it should be plus sign phase. Okay. On the other hand, here you have the transmitted photon. So, according to our convention, this is plus, but this is minus. So, therefore, we will have a -1 phase.
How both are transmitting.
That is what I said. This is these beam splitter, one should be careful, is that this is not a very this is something you will have to take. So, if I look at the microscopic description of beam splitter, it is not that the input beam and outgoing beam they are behaving in the same manner. So, one way is, so this is just a phase convention, I can take any other phase convention also.
So you are saying that if both reflect then it's +1.
Yes,
If both pass through it's -1.
both transmit is minus. Yes, yes.
And what about other two combination?
Yes. So, other one, you see this one, this is reflect, this is transmission, this will be -1, this is transmitted, this is reflected, this is +1. This is just a phase convention. Okay, you can take any other phase convention, that does not matter. In fact, I can explain without using this phase convention also. So, you do not have to use this phase convention, I am just using it to make life easier. So, if I do not take phase convention, still you know that these two contribution will get cancelled, right.
Yeah, because they are identical.
So, if you remember, the way we obtained it is a, what was that, a dagger plus b dagger by √2 and then a dagger minus b dagger by √2, something like that, right, acting on 0 0, I guess so. This is what you got. So, you see that what are the terms that you can delete. So basically this minus A dagger B dagger by 2, this one, and plus this is again same thing, B dagger A dagger is same as A dagger B dagger by 2, this is on 0 0. Okay, so you see that there is a difference in phase. No, no, this B dagger A dagger is same as A dagger B dagger, you know, that is.
No, no, that is okay. No, I'm saying that your expression is A dagger plus B dagger, A dagger minus B.
Yes, there is one more term, A dagger square by 2 minus B dagger, no, yeah, minus B dagger square by 2.
Right.
This is acting on 0 0.
Then it will give me 2 0.
Okay. So this is the term which is giving rise to this one. Remaining two, you see, they are in opposite phase and they get cancelled.
But I still did not understand the phase convention. How the fourth thing is plus 1.
So as I said, my phase convention is, if you know photon passes through from left side to right side, it will acquire a negative phase. No other path will acquire a negative phase.
Okay, so this is the convention.
This is the convention.
Inspect. What about left side? If it is goes left to right, then it is a minus.
Only from left to right it will acquire a negative phase.
Okay, yeah, that's the correct. Yeah.
Yes. That is my phase
Yeah,
convention.
then it is correct.
I mean, you can even explain things without using this phase convention. Then you will have to look for what are the terms you are cancelling. Then, I mean, you will have to bookkeeping. You will have to have bookkeeping of these terms to record that what are the terms you are cancelling.
This convention seems a little bit weird. Like, why?
It's okay. I mean, this is. I mean,
Why did you introduce this thing?
no, no. Just see. For this case, this is simple. But if I take, for example, 2 photons here, 2 photons here, I'll have to keep track of all the terms. Okay, so that is why I'm using this phase convention. So this phase convention will work even for other cases also. Okay.
And probably you explain it. What are the underlying philosophy? Because
So apart from, so forget about the phase convention. These two paths are indistinguishable. Why? Because when the photon comes here very nearby, then whether this photon will take this path or this path, we don't know. Similarly, this for these photons. Okay. So therefore, these two paths are indistinguishable. So they will not contribute. And why they will not contribute? Because they are coming in opposite phase. Destructive interference. So they are coming in opposite phase. So therefore, they will not contribute. So this is an interpretation of what is going on. Phase convention you can forget, you know, that if you calculate this thing, you know that these two terms will get cancelled.
but how the only thing I am facing difficulty to understand how phase convention helped me to understand what was.
So if you have phase convention, if you forget about this, then you know that this will have plus 1 phase, this will have minus 1 phase, otherwise amplitude wise they are same. So therefore, this and this will get cancelled with each other. Because we are dealing with, yeah, yes.
But there is a possibility that it could cancel from this in second to fourth. Also.
No, see, at this region which is inside the beam splitter,
Right.
how to distinguish these two phenomena?
How do I distinguish these two phenomena? You cannot.
You cannot, right?
Oh, okay. On the outcome level, they are kind of different. Okay,
Yes.
I see. Yes. Okay. Yeah.
So these two features you cannot distinguish.
Hmm.
You see, this you can distinguish.
Yeah. Just looking at the detector, I know
Yes.
that these are different. I see. Yes.
Okay.
Okay.
So therefore, because of indistinguishability of photons, when their wave function overlap inside the beam splitter, and we are dealing with 50-50 beam splitter, of course, you will not have a term like one photon is being detected here and one photon is being detected here simultaneously. Right? And you see that this phase convention also helps us to figure out these phases. Otherwise, we will have to do all the terms and keep track of all the terms and figure out what are the phases. But anyway, so this is fun, right? That inside the beam splitter, you cannot distinguish between this event and this event.
Will this phase convention also help us if there are multiple input?
Yes, yes,
Photons,
exactly.
like 3 in one of them or 2 in other.
No, I mean I'll have to take, this is about symmetric case. So like 2 photons from this side, 2 photons from this side, 3 photons from this side, 3 photons from this side.
So, but in that cases, schematics number will also increase.
Exactly.
So,
Exactly. Okay.
I see.
Right. Okay. So now, without going into all these detailed calculation, let's say I have 2 photons, then here it is 2 photons. Okay. So then, what will be the result? I think this is
There are 5 possibilities.
1 upon 2 factorial.
Yes.
This is square, right?
Right.
I think that is the, and then you can calculate exactly what is going on. Okay. So let us now erase this part.
How do you know there are 5%?
Like 0, 1, 2, 3, 4. 5 in one.
But some can cancel.
Yeah, but overall,
Oh,
because it's indistinguishable,
Oh,
you'll have 0 particle in one mode, 1
right.
particle.
That is true. That is true.
Okay. Yeah, now there are several cases. So,
For example, 0, it's like 2, 2, right?
2, 2, yes.
So 0, 4 will have plus sign. 4 on the right upper side. If both of them pass through left side, and minus sign plus. So 0, 4 will always have plus sign
0, 4, dollars and plus
in both the cases. This phase convention still gives us the correct answer.
okay, this is one possibility.
Right.
So this is our 4 0, right? According to our convention.
Okay.
Both minus minus cancel.
Minus minus. Yes. This will give you plus 1 phase.
Plus, yeah.
So this is plus 1 phase.
This phase convention will not work certainly for odd 3 2 kind of situation.
Yes, of course.
Yeah.
It will not work.
It will not. No, see, it will not. No, it will work. But the question is that that case is difficult to deal with because you will not have such symmetric situation.
But I mean, in
You
principle,
can
one
possible do.
and this
You
phase
can
convention will work there.
Yes.
Will it work for superpositions? Like if I take 1 1 plus 2 2?
Yes. It should work, but then it will be more difficult. Okay. It should work. Yes. So this is what will be my phase.
This is everything unaltered. Like
So plus 1 phase.
Plus 1.
And this corresponds to 0 4, right? This is plus 1 phase.
Yes, that's what you were saying.
Okay, right?
No, it's. Now there are 4 ways to have 3 1.
Yeah.
4 is to 4C3.
No, it's the same diagram. 2 2. You're talking about 2 2. Okay.
Yes. So this is what will be the phase?
So this is not correct, sir. 1 2 lines should come from left. Both are all are coming from left.
Sorry.
Right.
Right?
Right.
Plus
1.
So this is plus phase and this corresponds to 2 2.
This corresponds to 2, yes.
and then there are many other possibilities.
Yes.
Too many possibilities. It's better to calculate that one, it seems.
So okay,
Look, because the camera is not moving.
Oh, is that so?
Camera is not moving.
Yeah.
Can you see me now?
No, I can't see. I can only see the board on the left,
Oh,
not the board on the right.
Which one is left? Which one is right?
I'm not able to see the, not able to see the board and you,
Okay. No, unfortunately, this camera is not automatic. Okay.
AI
it's
is
not sensor based?
No,
Oh,
I don't think so. No, I may be wrong.
Because every time he says that the camera isn't working, then somebody connects it from
Right. So it doesn't. It is not automatically. It is moving. Okay. In principle, it can be done, right?
that's what my belief is.
With current technology, it's possible.
Yes.
I mean,
It's a simple motion
ARK
detector.
one.
Huh?
Yeah, ARK one.
It is
That
there.
one has the sensor, yes. That
But
one
there's
has-
just one board in two boards.
It should have a sensor. Movement sensor. Yeah. Anyway, so so this is
This is again plus 1.
plus, right, and this corresponds to 2 2.
The only problem is 3 1. There you will get the.
But is this 2 2 case exhausted?
No. So, no, there are more possibilities.
I think it will be 0 in the end. For example, here it's
What is the
minus.
four?
This is minus.
What is the 4C2?
4C2.
This is minus phase, right?
Yes. And then there's a similar diagram, but
Yes.
There must be 6 combination, right?
Yeah.
it is the same.
Too much of combination. I could have kept it.
Yeah. Again minus.
2 more terms for 2 2.
Yeah, exactly. 6 combinations are there.
Yes. 2 more terms will be there.
Okay.
So what will be other forms?
I think the
This line. It's coming. Okay, so this can go. This will, and then this can go. This will
these
have.
two never intersects. Yeah.
So this is -1, right? And then one more term.
The left one would be intersect. Yeah. Exactly.
Again -1. This is 2 2. So basically, overall, you will have a 2 2 term with negative sign.
Right.
Okay, because all these are equiprobable. Okay.
Okay, so we can also then infer the amplitude, not just the sign. Like
Yes.
here, it will be twice the amplitude of 4 0.
Yes. Right. So this is the thing. Now let us look at 3 1 and 1 3. How many terms will be there?
4 possibilities.
4 possibilities. Okay. So let me erase this part. Let us keep this thing. Now 3 1. 3 on this side.
Now I understand the binomial one.
Huh?
Now I understand the binomial one.
Yes.
Like if it will have m and n, then that is a binomial expansion.
Exactly.
Then minus sign theta, right?
Huh?
Then minus sign theta.
No,
That's
that on the left hand side, you have the explicit analytical expression, right?
Yes.
It will have a dagger plus b dagger to the power n and a dagger minus b dagger to the power n sum.
Yes,
So
yes.
if you expand it in binomial, then the coefficients will arise
so
automatically.
that m minus the coefficient of b in the second term is the number of minus sign theta.
Yeah, that is the
And that minus b is basically coming from that minus sign theta with theta equal to pi by 4.
So in this case, yes.
So that is the root of the.
This is 0, right? So 3 1 is 0, right?
2 other terms are there, and that should come with plus phase.
Yeah, because if you are going down, so only one particle can go down. So the other pair has to be negative.
Yes.
and then
What other here? There is only one
It will
line which
cancel
goes
out.
from left to right.
it will cancel out basically. Other possibilities will have both lines going right, so they will come with plus sign.
The possibilities are both lines going to the right. You're saying. Okay.
This will also have 0. 1 3 will also have 0.
Okay.
Let's see.
So you see that 3 1 and 1 3 term, they will get cancelled. Okay. Because 1 3 has both positive and negative. Similarly, 3 1
So you are
has,
saying that if even come in, the odd combo will always be 0.
in this case, yes. This case, yes. So therefore, you can now figure out that the state here. So this state in this 2 2 case, it will be some factor 1 upon root 2 4 0 plus 0 4 and then minus some factor. This factor we will have to figure out. This is 2.
We know the factor 2.
Yeah, that has to be figured out. Yes, yes, that we can figure out. But this is the form.
Right.
So you see that
So 1 3 and 3 1 are different states, right?
They will not cancel among
There
themselves.
will be extra 2 more terms.
They will
for
cancel
3-1
within.
and 1-3.
within them. Yes. I mean, if you have confusion, you can just explicitly do this
Yeah, that's what I'm thinking.
and do that.
That is the best part.
Yes. So what you see is that, again, unlike in the classical case where you have all these possibilities, but here you don't have this possibility of 1 photon here, 3 photons here, or 3 photon here, 1 photon. That possibility is not there. Okay. So again, this shows a typical quantum feature which is not there in the classical world. So in the case of one photon, it is very, very prominent, but even if you go beyond that, still this is present. Okay. Right? Okay, good. So now it is your wish to take more photons here and see what is happening. Every time you will get to see quantum feature. You will get to see quantum feature. Okay.
The sign convention is only true for like the 50-50 beams.
This is 50-50. If it is not 50-50, then you will not have this symmetric behavior. Okay. Now I will mention briefly. So this was, I exactly don't remember when was this done. Is it something like 80s, 84, 85, something like that? This Ou Mandel experimentally?
85.
85. Thank you. Yeah. And you see this Leonard Mandel was an experimental optics person, and how he revolutionized the field that one can figure out. He was perfectly an experimental person, and he is considered to be quote unquote godfather of quantum optics. Okay. I mean, unfortunately he was not alive. I am sure if he would have been alive, he would have given Nobel Prize. I mean, people smaller than him got Nobel Prize. Okay. So he has revolutionized the field. Okay. Okay, so they Mandel and his collaborators, they experimentally verified it, and this is, as I said, this is very, very important aspect. Now, so this is something which we need to look at it more carefully, that I think 1999 or 97, I do not remember, this is somebody called Shi and his collaborators. Okay. So, what they have done is that they have done a delayed choice experiment. Okay. So, if I look at this Ou Mandel effect, so this is your single photon, this is your single photon, and then you have this outcome. Okay. So, what you do is, in order to have this Ou Mandel effect, they should come together, these two paths, they should impinge upon simultaneously, otherwise you will not get it. So, you put a delay line here, so something like this. How will you do that? There are different ways. You can actually send the photon in a longer path, and so that they will not come together. You can put a phase shift here, that you can do, and then either in this path or this path, maybe here you put another delay. Okay. So, if I put, let us say, if I put this delay here, then of course, I will not get to see this effect, like so like 2 photons here, 0 photon here, or 0 photon here and 2 photons here. This is not present. You will have some kind of coincidence if there is a delay. Okay. So, you will have also the case where 1 photon is being detected here and 1 photon being detected here. This is possible if you put a delay. How much delay you will have to put, that is a separate issue. Basically, you will have to put a delay which is larger than the coherence time of this light. Okay. Coherence length of the light, sorry. But the point is that now what I do is, now I put another delay here, okay, in this path, or maybe I can put in this path. And if I choose these delays in such a way, and I think this, this delay will be double than this delay compared to this delay, then you can again you will get to see this effect. Okay. Yes. So, this is very puzzling to me. Initially it was really puzzling to me, that if you put delay, of course, you will not get to see this deep, which is understandable because these are not coming together. But then if you put this here also some delay, which is of course a relation is there, I think this delay should be half of this delay or something like that, then you get to see again the similar deep. Okay. And this has been done experimentally by these people. I think it is PRL 1999, okay, if I am not wrong. So, now if we want to think about that, so this delay you can think of like you are sending this to a longer path, or you are putting a phase shifter here, so that is equivalent. Question is, how will I explain it with this picture, that inside the beam splitter you cannot distinguish between these two paths. So, how will that, sorry?
Delay, the polarization of this photon is same throughout the experiment. It is not changed by the delay.
Yes. No, it is nothing to do with polarization.
I am talking about like if the polarization is same, they are indistinguishable had they come together.
Yes, but they are coming not together.
Okay.
Yeah, that's the puzzling part.
So, therefore,
but in the lower arm,
yes,
it could have been photon 1 or 2. Either of them could have crossed through the lower arm.
yes.
So, adding a delay there, how did it again make it indistinguishable?
Yeah, that is the problem. So, how did it, whether it makes it indistinguishable or for some other reason it is happening, that is what we need to understand. Okay. So, this idea of path indistinguishability is difficult to use here when you have delay, right, because these photons are not coming together. Yeah, so to me it is still puzzling, so I will have to think about it, what is going on. I guess it is basically the non-classical nature of light that is playing a role, because these are non-classical light. Through this thing, it will produce some sort of entanglement even if they don't come together, and once they create entangled state, if you put this is called delayed choice experiment, okay, then it may affect the statistic. Yeah, so if this is unentangled, then it will not affect anything, whether you put delay.
Those two paths which are going to the detector, they are unentangled.
If they are unentangled, then if you put this delay or not, it doesn't matter. But if they are entangled, then this delay, you can put this delay. So this delay will affect the correlation.
But even if the delay was not there, then it should affect the correlation as well as produce.
No. See, the thing is, well, point is this is what I need to understand, and to me it is not still clear that what should be the physics behind it. I mean, if I calculate things, it will come, but that's not the question. Question is what physics is going on. The spark indistinguishability, I think I cannot use it.
That is true. And if the correlation is your argument, I am saying.
Well, I'm guessing that perhaps correlation is my argument. It should be the argument. Otherwise, what else I can think of?
No, but that is a different argument. I am saying even on the face of correlation, it also does not
Perhaps,
because.
perhaps, yes.
Yeah.
But this has been done and experimentally verified. This is the case. In fact, if I do the mathematics, it will come. The problem is that what is the physics behind it?
So probably within the mathematics we should.
Sorry?
Within the mathematics we should find something. Let's see.
So I just need this clarification. Are we looking at like these two photons reaching there at different times, or just
Yeah,
with
different
different
times.
relative phases?
No, different times.
Not just with different relative phases.
Different times.
Okay.
So you are putting delay line means they are coming at different times.
Yeah, but I wonder if that just means that one of them was created earlier and the other got created later, but they happen to reach the beam at the same time, so one has picked up more phase than the other. And now there's a relative phase. Yeah.
Well, see, effectively, you can change relative phase or you can put delay lines, they are effectively same. So, if you put delay lines, its effect on the state is to put a phase, relative phase.
Yes.
So, effectively that is the case.
But even then, I mean, I'm still confused about whether we are really looking at a scenario where they don't arrive at the same time. Because it is possible that one was created earlier and the other was created later. So the one which created later had to start
No,
smaller
in
earlier.
experiment they have actually made it clear. I mean, they have made it clear that these two photons are coming at different times. So that they have made it clear.
So what is this delay time? Is it like there's a bound on this delay time?
Yeah, so the thing is that it is not that they should come here, I mean, dotted time, at same time. I mean, there can be some little bit of delay. That is not, I mean, in experiment, of course, that delay is there. Question is how much delay you can allow. So, the interference of these two photon paths should be allowed. Like this can come here and this can, maybe it will come here. Still interference can happen. But, if it is very far, then such interference will not happen. So it has to do with something called coherence length of light and all that. Okay. So basically, this delay we are inserting this delay in such a way that these paths, I mean, there is no scope of interfering, destructive or constructive. Okay.
If we put a delay of let's say 1 day.
Yeah.
And also on the lower arm another delay of 1 day.
Yes.
Then we will see one kind of setup. Like one photon here and one photon there, we will still see it.
Well, then you will have to make it sure that within that 1 day period there is no other light coming in.
Yeah. Let's say we make that. Then it's possible that we will see 1 1. Although of course 2 0 also we can see.
Yes. So that's what I'm saying. If you, put this delay reasonably, they should be connected. Then you can revive this deep. Okay. That's what this experiment is talking about. So I still need to understand what is the physics behind it. I'll have to go through it. I hope that this is because of some kind of non-classicality, yeah, but still I need to understand it. Okay. So this is bit puzzling, you know. The picture that we spoke about, like indistinguishable paths, that is apparently is not holding here. Okay, good. So maybe I'll give you the reference of that note. It is not here. I'll send you. Okay. Sorry. This math I'll not do that. This math because I'll have to first understand. Math is simple here, but the question is you'll have to understand the physics behind it. Okay.
Even I'm saying I just want to see it. What I can see.
Yeah. So the thing is that how to introduce this delay, that mathematics need to be used here. Okay. Other than that, things are simple. So basically, you'll have to use some kind of phase changes. So this delay, it means that let's say this is the B field, then you'll have to change it to e to the power I phi b, something like that. Okay.
But that is not surprising. The surprising thing is in the lower arm when you are putting the delay.
No, this is not particularly. So I may be wrong. I mean, this may be either here or here. I don't remember. Somewhere you will have to do. Yes.
Lower arm or the anyone.
So that if it gives rise to, let's say, phase change of -1.
Yes.
So we had two diagrams, both crossing through and both reflecting,
Yes.
and there has to be destructive interference between both those. So if this phase is not exactly -1, let's say it's -1. So if both are crossing through, the upper photon will have -1 phase, and then another -1 which will make it again 1. So no change.
No, but then you are not treating the indistinguishability.
Just to complete it, the other way is that upper photon gets a -1 and reflects, left photon also gets a -1, so both are again on the same footing. Yeah, so I think something to do with that, but yeah, what are you saying?
I'm saying that then you are not treating the indistinguishability. They're distinguishable anyway.
I'm treating it right now distinguishable,
Right.
and then
Yeah. Let me skip this thing. I'll do that thing properly.
Because you provoked us a lot.
Yeah. Yes.
Now
Right.
you are
Right.
skipping it.
Yeah.
What is the reference?
Yeah. I don't remember. See, the
PRL
C 1999 PRL. I'll have to.
In that paper also the calculation has been done, is it?
Kind of. These are experimentalists. They don't give
Yeah,
proper
exactly.
calculation.
I just want to look for the calculation.
Calculation can be done. It is not a problem. Anyway, I'll do that. But okay. Yes. So this I just mentioned to provoke you that this picture of indistinguishability of paths may not be the appropriate one.
I don't know. I'm not convinced.
If we want to make it is appropriate, then we'll have to explain this experiment also.
There must be some explanation.
Yeah, of course. I mean, to me it is still not clear. Let me put it in this way. Okay. Maybe Balakrishnan, can you hear me?
Yeah, I can hear you, Professor.
So this experiment, I don't know whether you are aware of. This is
I've heard of this experiment.
Yes.
Even G has done it. Even Scully worked on some theoretical aspects of this problem.
yes,
Marlan Scully.
yes. But did you follow what I wanted to mention here? That these indistinguishability of photon paths inside beam splitter, 50-50 beam splitter, when you talk about this Ou Mandel dip. So if you put these delays accordingly,
Yeah.
the incoming path and the outgoing, one of the outgoing paths, I mean there are some relation between these two delays, then you can again see, we know that if the two photons are not coming simultaneously on beam splitter, 50-50 beam splitter, you will not get to see the deep, right?
That's correct. That's correct. So the delay, as long as experimental delay is longer than the coherence time of the two photons, as long as delay is within the coherence time of the two photons, you will see a dip like the full width at half maximum will can still be measured.
Exactly, exactly. But if it is beyond the coherence time, then you will not see the dip.
Yes, you won't see the dip and you would get coincidence counts instead
Exactly.
in the lab.
Now this experiment of Shi et al. What they have shown is that if I put a delay, so that which will take these two incident photons beyond their coherence time, so that you will not get to see the dip. But then in the output, one of the output ports, you put another delay. Okay.
Yeah.
And then of course, depending upon how much delays you are putting input in the input and output, you will get to see again this dip. Okay.
So this paper I not read. I will read this paper carefully and then share my thoughts with you, Professor Ghosh.
Sure, sure. Yeah, yeah, yeah. Okay. Perhaps, yes, yes, yes. No, this delayed choice experiment is there for a long time. So, I have nothing to say about their experiment and all that, which is correct. Question is this picture that we talked about, how it should be applied there. Okay, good. So, now, so this was about the beam splitter and all that. Let me go to this other gadget which is called squeezing. This is also Gaussianly preserving transformation, squeezing. So, I think I discussed about the single mode squeezing. Which takes your quadratures, let us say x to the power maybe minus r, r is the squeezing parameter, and p goes to e to the power r, okay. So that they satisfy the canonical commutation relation. And so, this I think we discussed that if you take a harmonic oscillator Hamiltonian p square by twice m plus half m omega square q square, then if you change this omega or the string constant, then you can introduce such squeezing. Okay. Right. And the Hamiltonian which will generate such a transformation, erase this part. So, this is a scaling transformation, this is a scaling transformation. So, the Hamiltonian which will generate such thing will be of this form, at r x p r by 2 plus E x. Okay. In the sense that if I take exponential of minus I h acting on x, and I will have to be careful whether this is minus r or plus r, we will have to see that. It should be plus r, I guess, right?
That depends on, yeah, we have to check.
Yes, so we will have to check it. Okay. This is a quadratic Hamiltonian, yeah. So, whether it is plus or minus r, we will have to check it. Okay. So, so this right, this is x plus 1 by factorial 1, what is that, minus iota h comma x plus 1 by factorial 2 minus iota h, and then I will have to look at the commutator of this. This is too difficult, minus I h cut and x, what is that? This is minus I r by 2 is x p plus p x comma x. So, this is x and p x. So, this is I r by 2 and then this is I. So, this is minus, okay, minus r by 2. So, then this is no minus r and then p, sorry, p. So, this is minus r by 2 p, okay, good, plus 1 by factorial 3 is minus I h. Sorry?
X and X will be commutative, right? X and P will give you
Oh, sorry, this is x, sorry, this is x. No, no, what is the problem? Oh, sorry. No, this is not correct, sorry. So, this is minus I r by 2, this is x p plus p x, comma x. So, this is minus I r by 2, this is minus I x, and then this will be, what will be this?
this one also same. Because anyway X is
Right, minus I x, right. Sorry, yes. So, this will be minus r x, right. Yes, minus plus minus r x, sorry. Yes, so sorry for this. So, this is minus r x plus 1 by factorial 3, this is minus I h, and then now we will have to look at this. What is that? This is, hey, what is going on?
everything is going fine. You will have a power series of things.
Yeah, no, see, my point is whether this is x into r to the power minus r or x r to the power plus r. So, that is what I mean. Yes, minus r, yeah, this is minus r, this should be minus r.
Oh, so first order term is minus. First order term.
So, this is fine, okay, x e to the power minus r. So, this is correct, okay. So, okay, good. So, this is my scaling Hamiltonian. So, this means that this is equal to e to the power minus I h x exponential of I h, and similarly this one is exponential of minus I h p exponential of I h. Okay, good. So, this is my h. So, let me write it here. The scaling Hamiltonian r by 2 x p plus p x, right. Okay. So, now
So what is this appliance called which does this kind of transformation? Squeeze.
this is called squeezing. This is single mode squeezing. Okay. So, if you now use this thing, I think it is, so if you use this x is equal to a plus a dagger by root 2 and p is equal to iota a dagger minus a by root 2, I think what you will get here is, I am not sure what will be this thing. Can you tell me if I use this, what will be the case? No, if I use this, what will be the result?
Or do you want some intelligent answer?
Yeah. Anyway, it should be something, maybe iota or something, I do not know. This is a dagger square minus a square, something like that, Some iota should be there, I am not.
Yeah, so it should be a dagger minus a.
It cannot be a dagger. No. I think this is, I think it is r by 2, something like that, right? Perhaps, because iota should be there, otherwise it cannot be Hamiltonian. Okay. Anyway, you can figure out what will be this thing. So, this is my squeezing Hamiltonian in terms of, so this is single mode squeezing Hamiltonian, right. So, now if I apply, as I told you, if I apply on the ground state of harmonic oscillator Hamiltonian, this one exponential of minus I h. Okay. So, then it will have basically n is equal to 0 to infinity, it will have terms like lambda twice n twice n. I mean this lambda 2 n will depend upon r, what will be the form of this. So, you will have only even Fock states. Okay. And you can in principle figure out what are these coefficients. If you have very much of energy, you can do it explicitly by taking exponential and all that, but that is a dumb way of doing it. Okay. So, what one should do is there are other ways of doing it. So, basically you should look at the the position wave function of this, and from there you can figure out what will be the coefficients. Okay. Because in that case this will be sum over n is equal to 0 to infinity lambda twice n x to n, and these are what? These are something like Hermite polynomials with some factor, exponential factor. Okay. So, from there you can figure out what are the coefficients. Okay. Good, but that is okay, that is fine. So, so this transformation, so you can look at here what is the, so where will this A go? A is your x plus I p by root 2, right. So, under the squeezing, let me call it as S of r. Okay. This is the squeezing, single mode squeezing transformation, which is a of course unitary transformation. So, this will go to x e to the power minus r plus I p e to the power r by root 2. Which one? This one, huh? Yeah, Heidegger square minus a square. So, now you can express it, re-express it in terms of a and b. So, this is your, yeah, by root 2, and this is your iota Heidegger minus a by root 2. So, I think this will be a cosine hyperbolic r and then plus or minus. No, so you apply the squeezing transformation, which is a scaling transformation, x goes to x e to the power minus r, p goes to p e to the power plus r. So, a will go here and then you re-express it in terms of a and a dagger x and p. So, what will be this one, plus or minus the coefficient of a dagger?
I think it would be plus, right? Because sin h are that e to the power r minus e to the power minus 1. That will compensate a minus a. Let me do it. Or maybe you can do it.
Anyway, so maybe I will write plus so you can check. Okay.
Yeah, that must be true. That's what I
Something like this, okay, right. And similarly you can say a dagger will go to a sin hyperbolic r plus a dagger cos hyperbolic r, right. So, a will go to this and a dagger will go to this.
No, e dagger is
Anyway, I mean you can check what is the sign, okay.
E dagger is coming as a cos h r actually, and A coming as a sin h.
Oh, fine. Are you sure?
that's what at least all reading. Maybe.
For r is equal to 0,
Hmm.
it always will be sin h.
No, r equal to 0 is just.
It is a
So it
Yeah.
should be.
cos h, right?
So, cos h should be, the only difference should be in the sign, whether it is plus or minus,
Yes, yes.
but a should come with cos h in the first one.
Yeah, that's right. A should come with cos h. I mean, whether it is plus or minus, that we have to check.
Yes.
I mean, if it is minus here, it should be minus also here.
Oh,
Anyway, that you can check. Okay, so you see that this transformation A at A dagger, it goes to like, so let me write whatever is written here. So look at this matrix. This is a 2 by 2 matrix. Is this unitary? I mean, you can think of it like in the phase space also, because it is in terms of A and A dagger, in phase space in terms of x and p, same thing. This is not unitary, but this is a Lorentz matrix. Okay. I mean, it is a proper Lorentz boost in 1 plus 1 dimension. Why? Because you see this determinant is plus 1, cos hyperbolic square r minus sin hyperbolic square r, determinant is plus 1. So, this matrix is an example of SU11 matrix. So, the metric is different here. Okay. And this is definitely a energy non-conserving operation, because A dagger A, will it go to A dagger A? No. Right?
SU11 is the what is the group of SU11?
SU11 is the group, but
Like what are the elements of this group? These are the unitary matrices, no, right?
it is not unitary. So, you take the Lorentz transformation, I mean proper orthogonal Lorentz transformation, which is like a boost, for example, in one space and one time dimension.
Okay, yeah. So it's not unitary.
Okay. So, now, so this is not energy conserving transformation. So, such transformation, although it is, I mean, it gives rise to quadratic Hamiltonian and all that. It is a canonical transformation, of course, that also you can figure out. But this is not energy conserving transformation, and such kind of processes are called active processes or active transformation, where your energy is not conserved. Beam splitter transformation is a passive transformation where energy is conserved. Okay. Now let us look at, it is not energy conserving, because A dagger A will not go to A dagger A. You can check from here. A dagger A is the energy, right? I mean intensity, you can say.
It's not a unitary process. The squeezing is not a unitary process.
Squeezing Hamiltonian is unitary, of course. That is what he said. But at the physical system level, actual physical system level, this is not energy conserving process. Why not? This is symmetry preserving transformation. I mean, on your physical space, why should every symmetry preserving transformation should be unitary?
Are you suggesting it's anti-unitary? I mean,
Not anti-unitary. See, what we will need to look at is the angle, right? So, Wigner's unitary anti-unitary theorem tells you that a symmetry preserving transformation means the angle between two states, it should remain same.
it must be unitary or anti-unitary.
It must be unitary or antilinear anti-unitary, right? Okay. So, the question is whether this is such a symmetry preserving transformation. This is definitely not energy preserving transformation, and therefore, at this level this is not unitary. So, think of it like a Lorentz transformation, a special case. Lorentz transformation is a physical transformation. Does it not have any unitary representation? Yes, of course it has.
So is this because this Hamiltonian H hat does not commute with the
free Hamiltonian of the system.
Oh, same speed, beam speed and Hamiltonian also. But beam speed and Hamiltonian, it is energy preserving transformation. This is not. So, Lorentz transformation is a symmetry preserving transformation, isn't it?
Right.
So, do we say that we'll have to go out of the Lorentz group? No. So, it is a special case of Lorentz transformation, which is a symmetry preserving transformation. And therefore, it will have a continuous group representation. I mean, why should everything be energy preserving?
Yeah, physically that means like to perform this operation,
You need to supply energy.
and
Yes.
that means essentially your system is not unitary. I mean, like your operation is not unitary.
This level, of course, it is not unitary. This is true. This level it is not unitary. But I told you that the Hamiltonian, which will realize this gives rise to unitary transformation, right?
Yeah, exactly. That's where my understanding is like fine. Yeah, this is true.
Yes.
You have
But yes, so in actual lab, when you want to realize this, you cannot realize in this Hamiltonian. No. Squeezing cannot be realized with this quadratic Hamiltonian in lab. So in lab, you need something called three-way process, four-way mixing process to do that. So that gives rise to cubic or quadratic Hamiltonian. But theoretically, this Hamiltonian will give rise to this transformation.
at A dagger level, it's not unitary. I understand.
Yes.
Okay. But anyway, any Hamiltonian can be expressed as a and A dagger in second context.
Yeah, but this is not, we are not talking about any Hamiltonian. So what we are talking about is quadratic Hamiltonian. Because unless you take quadratic Hamiltonian, your Gaussianity will not be preserved, Gaussianity of states. So we are only considering all these processes, we are considering quadratic Hamiltonian.
This is true.
So it is true that to realize squeezing, I mean this Hamiltonian you cannot realize. For squeezing actually you will have to go to something higher order Hamiltonian to realize in experiments. And that is why it is a non-trivial process.
Higher order means you are saying more than quadratic order of A and A.
Yes. Okay. So anyway, so now the point is that this is single mode squeezing, and I mean this has nice properties. Like if I look at the Wigner function of this single mode squeeze vacuum state, it will be Gaussian. Okay?
A and A dagger is anyway not Hermitian.
Yes. Yes, it is not Hermitian. Yes. So this is one can figure out the Wigner function. This is a Gaussian Wigner function, just like coherent states and others. Okay. Now let us go one step further. Let me talk about two mode squeezing. By the way, here we are dealing with squeezing and anti-squeezing. So if you look at the what is that called, square of this times delta p square of this is equal to the 1 upon 4, okay, the minimum uncertainty. Of course, this will be much smaller than the uncertainty for coherent state, position uncertainty, and this will be much higher, but their product is 1 upon 4. Okay. So, so what now this two mode squeezing is something like this. So, you have two modes. So, I will call it XA, the quadrature, position quadrature corresponding to the mode A, plus x b. Okay. So, then under these two mode squeezing, which I will call S A B R for example, then it will go to e to the power minus r x a plus x b. Well, this plus or minus, whether it is plus or minus, or it depends. On the other hand, if you take P A minus P B, this will go to e to the power r P A minus P B. Okay. So, this is what you will get, and vice versa. So, if you take here minus, it will be plus, and so on and so forth. So, so you see that this is a kind of generalization of what we have seen here in the case of single mode. Okay. And one thing I forgot to mention is that this transformation is not necessarily to x and p. I can have a rotated quadratures also, there also you will have similar thing. Similarly, here you can have a rotated quadratures and do that. Okay. So, the Hamiltonian corresponding to these two mode squeezing, it will look like something like this. So, again I may be wrong at something like this, maybe this is my iota may be there. So, this is A dagger B dagger minus A B. Okay. So, R is called the squeezing. So, this transformation, this is again a scaling transformation. This transformation is achieved by such a Hamiltonian, and then you can basically look at it. Okay. Yeah, come. Yes. So, then so these two mode squeezing. So, again you can apply the exponential of minus I h a b, let us say h a b, and then on 0 0 you will get a two mode squeeze vacuum state, which is again n is equal to 0 to infinity. This time it is not like even Fock states, it will have some factor, we will have to figure out, this is n and n. So, this is kind of perfect correlation, not exactly perfect correlation, kind of perfect correlation, and this depends upon your R. So, if I take R squeezing parameter going to plus infinity, then this state will be your this so called EPR state. This is the position momentum state, okay, which is the joint eigenstate of x, joint eigenstate of this. So, anyway, so what we will see next time is that these two mode squeezing and single mode squeezing, they are intimately related. So, if I use beam splitter and two single mode squeezing in the opposite direction of squeezing, then I will get two mode squeezing, okay, and vice versa. So, once you achieve single mode squeezing, it is easy to achieve two mode squeezing. Okay. So, I will stop here. So, next
Hello?
time, yes,
Sir?
yes,
This Sanam sir.
yeah, this will start now. Okay.
Oh, okay, sir. Then later I will ask them.
What question?
Actually, this orthogonal, this Lorentz transformation you introduced.
Yes.
So this thing has some connection with this local filtering operation, right? This like they are also see this
Yeah.
transformation.
Yes, that is true. Yeah.
So
That is
they
true.
are also like this squeezing and this local filtering.
So, local
has-
filtering you apply this SL2C transformation. Okay.
Okay.
Yeah. So, right. So, which is basically area preserving transformation.
Okay.
Yeah. Okay, then I will stop here.